I think we have enough folks, so let's get started. My name is David Koick. I'm the Chief Scientist of Ocean Visions, and it's with great pleasure today that we are hosting Max Chalfin, who is from Running Tide Technologies. Max is here to talk about Running Tide's ocean-based carbon dioxide removal technologies and all the work that Running Tide is doing to advance our understanding about the capacity of the oceans to contribute to ocean-based carbon dioxide removal. A little bit about Max. Max has been with Running Tide for about 3 years now. And for most of those 3 years, he was the Director of Research and the Chief Technology Officer. He's now on the Board of Directors of Running Tide. And we've had the pleasure of working with Max for the last several years, most recently through our Launchpad program, which is Ocean Vision's program to provide technical advising and assistance to ocean-based carbon removal startups. Through this Launchpad program, Ocean Visions was able to set up an independent scientific advisory board for Running Tide. And it's also given us the opportunity to engage with lots of other startups in the ocean CDR space. We are actually accepting applications for a second cohort of the Launchpad program right now. And so if you are part of an ocean-based carbon removal startup and think that you could benefit from technical advising and assistance, I would really encourage you to apply. Before I turn over the microphone to Max, I just wanted to let you all know this is being recorded and we will make this publicly available as soon as we can, likely within the next several days. So just know that that's a question that we get often, and it will be posted on our website and shared through our newsletter. And without further ado, let me turn it over to Max. Max is going to speak for about 25 minutes. Please record your questions in the chat. We will be reviewing those questions and monitoring those questions. And then afterwards, we'll moderate a Q&A session with Max so that folks have a chance to ask him questions that arose either coming into the session or during Max's talk. Okay, Max, take it away.
Great. Thank you for that kind introduction, David. Thank you to Ocean Visions for inviting us here to talk. Thank you to everyone for tuning in. So yeah, let's just go to this next slide that has a little table of contents, brief. So the motivation for this talk, Running Tide, we published our research roadmap on our website. There's a link here, and I think there's also one in the chat. This is in a lot of ways kind of like an itemized list of collaborations and projects. And so we wanted to take the opportunity here to just provide some context, that context being sort of like, what does Running Tide do and how do we think about the problem of ocean-based carbon dioxide removal? And then to touch specifically on certain scientific research avenues that we pursue, the biogeochemistry of the oceans and the Earth system, and then in some depth on our approach to ecology and the way that we are pursuing environmental impact assessment. And a note about timing, I have some anxiety about the timing here, just because I could talk about every one of these slides for like hours. So I'm going to try to move quickly here and leave some healthy time for Q&A, and then hopefully maybe audience questions can direct us to how we want to spend the time of the discussion. Okay, let's go to the next slide. So what is Running Tide? For better or for worse, Running Tide made a public debut into the ocean carbon removal space in 2021 as a kelp sinking company. That I think is really a sort of very narrow representation of the broad approach to ocean-based CDR that we pursue. So I just kind of wanted to take the opportunity here. If you know of Running Tide as a kelp company, maybe we can try to start with a blank slate. And if you haven't heard of Running Tide before this talk, then just forget I mentioned this at all. Okay, let's go to the next one. So Running Tide pursues ocean-based carbon removal. And specifically, the way that we do this is by developing a mechanism of these passive drifters. Here's a picture of one kind of puck-sized object with some kelp, admittedly kelp growing off of it. The idea here is that we are trying to use this mechanism to spread an intervention over a very broad area of like an entire ocean basin. And that intervention is designed to cause a chemical change to the ocean. And when I say chemical change, we're talking about, photosynthetically uptaking DIC or adding alkalinity. And these pucks generally are also synthesized out of terrestrial biomass. So that's like crop and forestry residues. So there's also an element of just sinking terrestrial biomass that occurs here too. And that of course contributes to adding a chemical change to the ocean, right? Because when this stuff ends up on the bottom of the ocean, it gets remineralized and that consumes oxygen. So that also changes the chemistry of that boundary layer. I put ocean fertilization on this slide because that is in the category of chemical changes to the ocean that could be pursued. Running tide does not actually do this work today. The reason for that is just because, the scientific consensus does not support, in our minds, actively pursuing this, as an industrial and commercial project. I will say that over the last 3 years, that we've been working in this space, ocean fertilization has moved from something that has been, reasonably taboo to even talk about, to something that is, getting a little bit more attention of the scientific community. I think that's really great to see. So this is an example of where we really take our cues from the academic community and would love to see, more engagement, more research on this frontier. Okay, let's go to the next slide here. Okay, so the mechanism that we use to actually cause this chemical change to the ocean, this ocean-based CDR, is these passive drifters, and we synthesize them out of several different recipes of materials, which I'll talk about in a moment. We place them in the ocean and we let them move under the influence of currents and wind. Once we let them go, we don't touch them again. And the way that we design these things when we build them is to try to tune their floating period, which is really based on the composition of materials that they're made out of and their volume. So you can see, I have this picture here. Ultimately, when we talk about tuning flotation, the ocean is a somewhat chaotic system, and ultimately flotation is like a Poisson process when these things actually lose their buoyancy and sink. So we reproduce through our investigations this distribution here of how many of these things remain at the surface of the ocean as a function of time. So you're probably looking at this picture of a handheld sized object and saying, okay, you're talking about making like a climatically relevant change to the ocean, which is going to involve moving a ton of mass. And then you're showing me this thing that somebody is holding in their hands. It seems like you're going to have to use an awful lot of these things, right? So here, let's look at the next slide here. So that is very much true. So here, what you're looking at is a picture of our current feedstock stockpile, which is, a pile of wood in Iceland. And just, maybe it's hard to see in these pictures, but we've, each one of these sort of red and blue block objects in the picture is a shipping container. So we've kind of used these shipping containers to sort of partition a little perimeter and to stockpile this material inside. So maybe that will give you a little bit of a sense of scale. And working with this material, and really trying to move the mass that is required to affect, relevant climate mitigation has been a really eye-opening experience for us. And it's changed the way that we think about this industry pretty substantially and think about our role in the industry substantially. Because you have to remember that for a carbon removal company, right, we can only mint carbon credits on the basis of our net change, to atmospheric carbon or carbon in the fast cycle. And so we have to be very mindful of all of the embodied carbon, throughout our entire LCA. So when you start looking at, the carbon that's emitted in shipping material around between different sites and the carbon emitted, in manipulating this material and producing it, you start looking for ways to defray the costs by making your whole process a lot more carbon efficient. So here, let's take a look at the next slide. Oh yeah, this was meant to be a little animation, so hit it again. Yeah, so in this process, here's some examples of some things that we added or are investigating in the case of enhanced weathering. These are just some specific examples. So, that site that in Iceland, had a lot of sort of diesel powered machines. And we've been looking into, the investment in replacing that machinery with electric grid powered stuff, which in Iceland is clean because of all the geothermal power they have there. And then another really interesting sort of idea that came out of this is we noticed that if we're shipping material, all of this biomass to Iceland, there's this backhaul where the shipping containers are not full. And what could we do to try to defray the carbon cost of this? And so one thing that we are looking at now is taking basalt from Iceland back to North America on those backhaul lines to look at using them to do enhanced weathering on roadways. So, this is very much in development, but the point that I want to make here is that, here, actually, let's go to the next slide, I think is where I will make this point. Yeah, so the point that I want to make here is that what we have found through the process of working through the logistics of actually performing carbon removal is that there are these two different systems at play that are overlaid on each other. One of them is the Earth system, right, which is cycling, in its biogeochemical cycles. It's transforming, mass, and it's trading off the motion of mass against the storage and utilization of energy. And then on top of that are all of these existing industrial cycles. What are the, how does industrial infrastructure move mass around? How does commodities flow through the economy? And so, what we have found is that carbon removal companies, we have to move a lot of mass. We have to leverage a lot of industrial infrastructure. And we have a very, very high internal cost of carbon because we have to do these fully accounted LCAs that net out how much carbon removal we're doing. And so we have a very high incentive to invest in decarbonized infrastructure. So this is a situation where I think, carbon removal and decarbonization have often been presented somewhat in opposition to each other, whether, that's through the lens of one creating a moral hazard for the other, or through the lens of, just splitting resource allocation between the two. But we are really finding that that these activities may very well be additive. So like one example that I want to give here that I think really articulates this is, when we want to put a lot of macroalgae seed out on these carbon buoys in the water, we need to cultivate that seed first. So we have these bioreactors where we're clonally propagating macroalgae starting material. And we need to feed those bioreactors with nitrogen, with fertilizer, right? And, right now we can just use off-the-shelf F/2, for example, right, which is just like algae food. And at the scale that we're at, that's okay but we still have to deduct the embodied carbon that it takes to produce that fertilizer. So if that's coming from a Haber-Bosch process, then of course, that's coming out of our LCA. So, maybe we could make that better by using, nitrogen that's been biologically fixed by, let's say, bioreactors full of nitrogen fixing bacteria. Okay, that's a little bit more carbon efficient. But those bioreactors are really hungry for sugar. And where is that sugar going to come from? Well, if it's coming from cornstarch, right? Then it's competing directly with existing agriculture, which we know is going to be something that is becoming more and more carbon intensive and less sustainable. So probably ultimately the way to really affect this is to start using coastal blue carbon macroalgae cultivation as a way to, produce the sugar and also, potentially also sequester carbon on its own. Now, we don't think, for example, that blue carbon macroalgae can scale on its own as a carbon removal apparatus to a climatically relevant, amount of sequestration. But this is an example of what we're really trying to do is tap into these cycles, into these biogeochemical cycles and these industrial cycles, and just find every little place where we can squeeze efficiencies out of that system and move the most amount of carbon out of the atmosphere. Okay, let's go to the next one. Yeah, okay, so then, that kind of mode of thinking has really kind of helped us articulate, to ourselves, like, what is our place in the world here, where you have all of these interconnected pieces. And, just here, you can hit the button again for this like crude animation of, running tide. Our role here is to sit between all of these, these pieces of, the natural systems of the earth and the industrial systems of the economy, and try to figure out, how can we put these pieces together in a way that optimally, mitigates the climate problem. So let's take a look at the next slide here. Okay, so what do we do? What do we sell? What is our product? What do we make? I think from a revenue perspective, it's easy to say, well, we ideally would sell these carbon credits, but I think that a carbon credit, when you really think about it, is a kind of an abstraction, right? It's a financialization. It is a consequence of performing a carbon removal activity, and so while ultimately it is the thing that connects a company like Running Tide to revenue, we don't really think of it necessarily as our product in a sort of product thinking sense. So let's look at the next slide. So we consider our product to be what we call the carbon buoy. That's the sort of passive drifter that we're talking about. And what we really like about this product is that it is itself designed to be something that can be optimized against all these different constraints that I've been talking about. So, the recipe for these carbon buoys is not really fixed, and we explore lots of different things here. And here's just a snapshot of, the different things we're trying and how ready we think they are. But, you could imagine you're going to be working in parts of the ocean that are more nitrogen limited than they are iron limited or phosphorus limited. And that may dictate, what type of macroalgae seed you want to put out there. Or maybe you're working in areas of the ocean where, the benthic boundary layer doesn't have enough oxygen to support sinking organic carbon at all. And so you really need to focus on a carbon buoy that's just going to, dissolve an alkaline mineral into the surface of the ocean and do ocean alkalinity enhancement, or maybe you're working in a part of the world where there just is not a ready supply of terrestrial biological feedstock, and you need to, build these things out of like a foamcrete type solution. So there are so many different constraints here, and the purpose of the carbon buoy is to allow us the flexibility of optimizing against them. Okay, so let's go to the next slide. Okay, so that's a lot about sort of like how we see ourselves and what our role is here in this industry and in this ecosystem of the industry. For this talk, to talk a little bit more about some actual technical research direction, I want to just kind of like tighten the focus a little bit. So if we can just, hit go to the next slide here, just to highlight, I want to focus on these sort of nature-based pathways, or I should say really kind of biological pathways, where you're relying on photosynthetic fixation to do your ambient capture, and then you're sinking organic carbon to the deep sea as your storage mechanism. And let's look at the next slide, David. And then similarly within this context, you can hit that button again. These are the areas I want to focus on. So the way that we think about this is, we're not the first to say that carbon removal is applied biogeochemistry, but these biogeochemical budgets of the Earth system are ultimately going to be the things that drive, the carrying capacity of these different carbon removal approaches. But ecology is also a really important driver of the decisions that you make in how to pursue this technology, and ultimately the scale that it can operate at. And then I'm going to touch on a little bit about engineering for MRV. It's not really the focus of this talk, but I do have a few things to say about it. So, all right, let's go to the next slide. Okay, so yeah, when we're talking about applied biogeochemistry, right, we're really talking about how do we sort of use these biological systems and these chemical systems to transform, chemicals into other chemicals in order to amplify the Earth system's ability to remove carbon. So when we source, for example, terrestrial biomass from a forest, we really want to understand how those forests work and how they sequester carbon. So a forest is like a really nice biological, pump for taking carbon out of the atmosphere and fixing it. But it's a really bad storage mechanism, right? Because obviously it can burn down. And specifically, a forest is a system that grows exponentially until it saturates in size. So you wouldn't ever want to clear cut a forest and throw it in the ocean. What you want to do is sort of sustainably harvest material out of that forest to maintain its growth at that sort of area right before saturation, where it's where the derivative to that exponential function is steepest, to maximize the forest's ability to remove carbon. And then, of course, the more you understand about these systems, the better you might think about making sure that the soil carbon and the mycelium networks in the forest are healthy. And so this is all kind of an important part of the approach that we take. And then, of course, on the marine side, at the surface of the ocean, you're transforming, limiting nutrients, whether that's nitrogen or phosphorus or iron, into the uptake of DIC. And then at the bottom of the ocean, of course, you're consuming oxygen, right, in order to remineralize that organic carbon that you sink. And so these budgets constrain, how much of this you can do, how much of it you can do at all, and then, within a ceiling of that, like how much of that you can do responsibly. So here, let's go to the next slide. So, our approach here is it's very, very difficult, right, to go measure everything in an open system. So the approach that we take is we look at, we try to study the chemistry, the physical and chemical changes that occur local to these carbon buoys. So here's a picture of a laboratory setting, but we also, do these in observational experiments in the water as well. We build a data set that's based on how we expect this to behave in these very local settings. What's also very important to us is studying this sort of ocean transport. When we put these passive drifters in the water, how are they actually going to move? Because that tells us, the spatial extent and also the density that we can expect to have these things be operating in the ocean system. And then we take those two things together and we overlay them into a modeling framework to say, okay, how will this actually cause a change to the Earth system? And then how will that perturbation to the Earth system actually unfold in terms of the net motion of carbon, from the fast cycle, the atmosphere on the surface of the ocean down to the deep sea. Let's take a look at the next slide here. Oh yeah, here's this, when we talk about MRV, I do want to touch on it. We've produced a lot of material explaining our MRV system over the last several months. And so I don't want to be too redundant here, but I do want to just identify, MRV is this like impenetrable acronym that has a lot of different meanings to different people. It is, this process of taking a carbon removal activity and rolling it into this like financialized instrument called a carbon credit. And that involves a lot of different things, right? It involves governance and auditing as much as it involves, the actual technical, oceanographic work that it takes to analyze these projects. And so, for example, when we announced that, we were going to use Deloitte to be our auditor, I think there was we got a lot of questions about like, well, that were sort of in the spirit of, what does Deloitte know that, the ocean science community doesn't know? And, I think the important thing to remember here is like MRV is a big tent. And this is not to say that, when we're using Deloitte to the exclusion of domain-specific experts, but also a lot of what we're doing is really just kind of industrial accounting. And there's no reason to reinvent the wheel there. So anyway, that's the sort of the high level thing, but the thing I want to focus on here is like within MRV, we have the actual technical work that needs to be done to to figure out how much carbon has moved through the Earth system, and we call that quantification. And our quantification approach is similar to our biogeochemical approach, right? And you'll see is similar to our ecological approach, which is you do a lot of rigorous testing in a controlled setting, like a laboratory, and then you do more testing in a less controlled setting, like a field site, and you build yourself a really good prior of what's going to happen in these more or less controlled settings. And then you take that intervention offshore. We develop these custom sensors here to evaluate what's happening out in the open ocean. But that evaluation is not meant to be our primary data set, right? That's like, we go in with a strong prior, and then that prior gets validated by the observations we make in the open ocean. And the reason for that is because, collecting data from the open ocean is necessarily going to be sparse. So it's not going to be able to substantiate the data set. And then, of course, all of that ultimately has to be fed into a model to really understand, how the Earth system is going to evolve once you make a change. So these pictures represent like a simple thing. That picture I showed you earlier about the float duration. What did we do? We took a bunch of these carbon buoys, we put them in these wave tanks, and we knocked them around for a really long time. And when we picked, we collected a data set that sort of showed us how these things sink. And then when we actually take them offshore, we do put some of them in these buoys where they can be imaged in the actual offshore environment. And that's how we reproduce this curve. Okay, let's take a look at the next slide. How am I doing on time here? I'm okay. Okay, so ecology. So, ultimately, we want to make sure that when we are like going out and making interventions to the Earth system, that we're doing, more good than harm. And that is a very, it's a challenging prompt. I think that when people talk about how, ocean-based carbon dioxide removal is, still very much a nascent area of inquiry, this is sort of the main piece of the puzzle that there are the most questions about. I would take that one step further and say that, ecology as a discipline is not, and maybe this is a controversial thing to say, but is not really prepared for the demands that are going to be placed on it, over the next century. The nominal consensus here, right, it is that we should, I've heard many people say, referencing the Hippocratic Oath and saying, first do no harm. But this invocation to do no harm is really doesn't resonate against a baseline that's deteriorating as rapidly as, the ecology of the Earth system obviously is. And so how do we structure, how do we create an ecological structure that can systematize our thinking around making positive interventions? And it's hard, obviously, there are a lot of technical barriers to this, just the complexity of these systems. There have been, countless examples of times that humans have tried to make changes and run into unintentional consequences. And I think that is, further complicated by the sort of, fundamental mistrust between, most ecologists and, corporate actors. And of course, there's always these political questions of like who has mandate. But look, when we talk about growing macroalgae in the ocean to sequester carbon, and that's not even where we are right now. That's what we're trying to develop. But that technology is like Stone Age technology, right? That is crude and inefficient. It is not the best way to get carbon to move through the system. Ultimately, where we need to be is in a place where we're really feeding the ocean, right? Creating an ocean that is, full of life, that is robust against these evolving changes of temperature and pH that are coming for it. And as we boost that primary production, ultimately that's going to boost grazing activity. That's going to ideally create a bountiful ocean that will be very effective at moving organic carbon, fixing organic carbon at the surface, and then moving it to the deep sea. while ideally also, providing like food and these other things that we need to support, civilization. Those changes are not going to be really framed as conservation or restoration, because they're going to have to be different than, than the existing baseline, than the pre-industrial baseline, simply because the ocean itself, the state of the ocean is changing so rapidly. Okay, so let's go to the next slide here. So what does running tide do in the face of this big open question about ecology? Well, when we go to do an environmental impact assessment, here is the structure that we've created. The first thing we do is we look at, all of the different exposures for risk. And, we have been very proactive about, this is basically like a super literature review, but it's not something we do in a silo. We've been working with Ocean Visions. We've been working with a number of other expert panels to just catalog all of the things that, basically could go wrong, right? Or all of the risks of harm that exist. And the scientific community has been extremely helpful in creating, in studying this problem. We catalog them in terms of architecture and scale. Architecture being, what's something that creates a risk at any scale, whether that's something like marine mammal entanglement or, introducing like an endocrine disruptor to the ocean, versus something that really is going to be scale dependent. So when you talk about something like attenuating incident light by creating too many floating objects, or reallocating nutrients away from phytoplankton, like this obviously depends on how much you're doing and how intensely. So then when we go into an actual project, we design the project, right? We kind of lay the specs of it. And it's important also to assess the region that you're doing that project in. And then we approach mitigation, which I'll talk about a little bit more in a moment, differently for these architecture dependent exposures and these scale dependent exposures. Here, let's, and then there is also this element of integration with basic research. There are a lot of, as I mentioned in the previous slide, there are a lot of questions about how to structure a positive intervention that people just have more questions than answers. And so alongside the what I would call like a very sort of conservative approach to scaling out our projects, which, the basic idea here is to start small and iterate out. We're also looking to support, basic hypothesis formation by working with other research partners to do, what is really more basic observational research. So let's move to some of the some next slides to talk about this very concretely. So, for mitigating these architecture dependent risks, basically it's the idea is to change the architecture. So, one of the things that we were talking about 2 years ago was trying to develop these micro farms, which were basically these floating kelp lines. And we spent a lot of time trying to make this design work. And ultimately what we found is that, first of all, these vertical lines caused a big marine mammal entanglement risk. But secondly, it was very, very challenging to create a logistically scalable, cost-effective way to control the buoyancy on these flotations that did not involve using plastics. And we could talk more about this. We tried a lot of different things, but ultimately we had to abandon this strategy simply because we did not want to put this much plastic in the ocean. Okay, well, let's go to the next slide. When we're talking about scale-dependent risk, that for us begins with this ocean transport analysis. We really need to understand how these things move, how these carbon buoys are going to move in the water, in order to be able to predict, how much material we can place in an area, in what season, in order to determine what the final density, and not just final density, but evolving density of these things will be, right? So for example, if you care about, light attenuation, you're going to start off with, a bunch of very dense material over a very small region of the ocean, and that's going to evolve into a much less dense concentration over a much larger region of the ocean. And so what we do is right now we are both our kind of computational experiments and our deployment experiments are very small in scale. We try to place a small amount of material, and we sample, lots of, we take a region of the ocean, we place it in lots of different areas, both in terms of, over an entire season. With the idea here is that we're just trying to collect as much data as we can about basically just these Lagrangian drift experiments. We need to get really, really good at the numerical, at the physical oceanography problem of determining how these things move in the ocean. And particularly that also governs, one of the main dials that we have on this is how long these things float for. So right now we work with material with these carbon buoys that are designed to sink, in a matter of like 2-ish weeks. That much shorter floating period obviously makes their motion a little bit easier to predict, but it really limits the amount of macroalgae, for example, that you can grow on them. And so that research arc for us is all about increasing this confidence interval in order to be able to perform this mitigation measure for these various environmental risks. All right, let's look at the next slide here. In situ monitoring. So what's really nice about this is that, the MRV stack that we've created, really does double duty here in terms of giving us the visibility into how these systems are unfolding in the ocean. I have a lot more to say about this, about the connection between MRV and ecological monitoring. I hope that that the entire industry can evolve into a place where ecological monitoring is much more of a integral part of the value creation of MRV, and less, right now MRV seems to be like primarily focused on just like counting how much carbon is removed, and then the sort of ecological environmental impact is, a secondary parallel process, through which you get a permit or something. But I think there would be a lot of value creation there if we could find a way to merge those together. And from a technical perspective, they really do involve like a lot of the same analysis. And so it feels like a really natural fit. Okay, let's go to the next one. Oh, yeah. Okay, so this is one of the places where we are really, I think, farthest ahead. And one of the reasons for that is just because of a lot of the incredible convening work that Ocean Visions has done on this question, which is, right now we are not really sinking terrestrial or any organic carbon with a lot of density or scale when you compare it to what's happening in the background of the baseline, the background of the region anyway. But we know that in order to really scale this this operation, we need to really understand what it looks like to the benthic boundary layer and to these benthic ecology when you send a lot more organic carbon to the bottom of the ocean. And so, we have set up a series of observational experiments with a few different partners to put our material on the bottom of the ocean and measure what happens. And measure what happens, of course, means a few different things. Our primary hypothesis is that we care about the degradation rate, the rate at which this organic carbon gets turned into DIC and oxygen is consumed. The primary ecological limit that we don't want to hit is depleting the oxygen availability. But there are there's obviously secondary complexity here. We really care about what do those grazing communities that actually come to eat this stuff look like? What are the byproducts of their metabolic activity? How do these communities change when you just give them a lot more food? Are there successional dynamics, and how are those changed with seasonality? What we would really, really love to see here is a whole of community effort to synthesize. There are so many different observations about organic carbon in the ocean, but our hypothesis is that what we really need here is to put this into some sort of like hierarchical framework where we can synthesize all of that data into a common data set to really try to understand, what can be known about these dynamics. So, okay, we know that organic carbon, if you when I say hierarchical model, I mean like you've got organic carbon, that's like your first pass. And then within that, does it matter if it's like a carbohydrate or a lipid, right? Or a protein? Within that, it's going to matter if it's of marine or terrestrial origin. And how can you sort of drill down, starting with the least complexity and getting to the most highest level of resolution, so that you can take these observations that span from, wood deposition in river fans to salt falls to whale falls, to the experiments that we're doing with macroalgae and wood, and synthesize this into a common state. That's the kind of like the level of community cooperation, intercooperation that we need to build toward, all of us together here. Okay. I think that might be my last slide, David. Let's try. Oh, yeah. Okay. Well, thank you for listening to that. I went a little bit over the time that I held for myself here, but we do have some time for discussion. So thank you.
Thank you, Max. That was really comprehensive. Really appreciate all the time that you spent to go into so much detail about so many of the things that Running Tide is doing. I think I'd like to start this Q&A here with a question that just came in recently from Ryan Hostak, and I'll just read it verbatim and then turn it over to you. Given that Running Tide intends to operate in the open ocean, i.e. non-coastal, how does Running Tide think about community engagement and outreach for these interventions?
Yeah, that's a really great question. So, one of the things that was sort of the motivating reason for being for Running Tide was that it was founded. So Marty Oblin, who's our CEO and founder, came from a fishing background and was heavily embedded in the working waterfront of Portland, Maine, which is where we're headquartered. And I think a lot of his personal motivation was just seeing the destruction of the economy of these communities, that mirrored the deterioration of the ecology of the ocean. So when we think about community stakeholders, our kind of thesis here is that you want to be, kind of hyper local and hyper global. So hyper global, I think it touches on a lot of the stuff we just talked about. Like everybody shares, the biosphere. We are trying to make a positive intervention for the oceans and for the earth. That's one North Star. When you're talking about working in the open ocean, you really need to leverage a lot of the expertise and skills of these working waterfront communities. One of the things that, we see, Running Tide's mission as a really great opportunity to revitalize a lot of these coastal communities that are losing out on some of their existing, economic support, simply because aquaculture and fishing has become so much more difficult. As we've learned more about this industry, sort of, and how this industry needs to evolve, in that pattern that I just kind of walked you through, I think that we've seen a lot more of the same here, which is like, oh, there's a real opportunity here to revitalize a lot of these forestry communities. If we took all of the latent forest land in North America and we ran it operated that land to the spec of sustainable forestry practices, which we know of, that would remove a lot of carbon, and then did this thing where we took the carbon out and stored it. That would store up a lot of carbon, and it would also create a lot of it would be a lot of job creation in these communities that that need it the most. So for us, the stakeholder engagement on the community level is very much a kind of part of the architecture. It's not like an afterthought.
Thanks, Max. Let's pivot to a question that Greg Rao asked earlier, which is all around the environmental impacts of Running Tide's process, and specifically, how do you maximize the amount of carbon that you sequester while minimizing the amount of nutrients that are tied up with that organic carbon so that you don't deprive existing ocean ecosystems of those nutrients? AKA, how do you not nutrient rob marine ecosystems?
Yeah, I mean, I think that that's really an excellent question. I think, ultimately, as I've said, these biogeochemical budgets are going to be the thing that constrain the capacity. One of the reasons that we like macroalgae, more than stimulating phytoplankton primary production is just simply that its stoichiometry between carbon and nitrogen and phosphorus is much more advantageous. So on the margin, if you could take, a unit of nitrogen and reallocate it from phytoplankton productivity to macroalgae productivity, like you're getting more carbon. We don't know this goes back to what I said sort of at the top of the talk. We don't know right now if we possess the industrial capability. I don't mean running tide, but I mean, our civilization possesses the industrial capability of replacing some of those robbed nutrients. But we don't know scientifically sort of what the effects of that will be. So I think that as we build out these systems, that needs to be a huge area of inquiry. And like I said, that's much more, I think, right in the foundational science kind of readiness level than it is for a commercial operator like Running Tide to take on at this point.
Let's move on to a question that just came through on the chat from Kaylee Sten, Max. And this has to do with an issue that's been getting a lot of attention recently, which is all around the lags and inefficiencies of air-sea gas exchange, right? So you do something in the ocean that's carbon, but it doesn't necessarily result immediately in an exactly 100% efficient removal from the atmosphere. So how do you think about that and how it affects the valuation of your sequestration approach?
Sure. How much time? I could talk to you about this all day. Okay, so when we are looking at this air-sea gas exchange problem, there are two different pieces of that, right? There is just the fact that there's a lag, right? If you do something today, all of that carbon is going to equilibrate over, the next, most of it in the next 10 years, right? So there's just like this, there's the lag piece of it. And then there's the other piece of it, which is this premature attenuation of the air-sea gas reequilibration, because some of that carbon depleted water will downwell and not be in contact with the atmosphere. So that second thing, that's real, right? Like you can't, the amount of carbon that you remove from the surface of the ocean, in terms of the embodied carbon in the biomass you sink, is just not going to be equal to the amount of carbon that ultimately that is additional, the motion of carbon from the fast cycle to the slow cycle that's additional because of your intervention. And you just have to, you have to take account of that and sell fewer carbon credits, like based on that haircut. And the scientific community, especially over the last year or so, has been very proactive about presenting ways to account for this. And so we're happy to see that evolution. That seems like that's the way it's got to be. As far as the first element, though, like what is the lag here? I think what's important what's important to keep in mind is that we're up against a problem that's going to take a century to solve, right? This excess of carbon dioxide in the atmosphere. And so when you're talking about these lags of a couple of years to a decade, from the point of view of the climate mitigation intervention, it's, I think it's acceptable. From the point of view of a financialized carbon credit product, it opens up some questions that need to be answered. One of the things that we look at here is just how inert the intervention is, right? So like if you do something today that's going to cause carbon to be removed tomorrow, you need to look at the risk of reversal in that interval. So like, for example, if you plant a tree, you're making it thermodynamically more likely that there will be a forest fire because you're adding more, more wood that can burn. And so you can't just plant a tree and take credit for all of the carbon of a mature forest, right? that isn't necessarily true when you make an intervention like this, where you're taking DIC out of the surface of the ocean, right? That system is going to unfold, and anything that would cause a reversal there, right? That could cause outgassing or something, is not thermodynamically more likely because of your intervention, and so that's part of your baseline scenario. So it's easier to say, at time equals 0 of your intervention, I've created an intervention. I have done this amount of additional carbon removal. So that's our perspective on that particular problem. But I do want to say it's very important when we talk about this air-sea gas exchange to tease apart those two different things, like the premature attenuation in one category and the sort of lag of the system in the other.
Max, I want to build on this with another question about MRV that comes from Veronica Tamzin, and I think is very relevant to a lot of the thinking from many folks. So I'll just read it to you. CDR providers like Running Tide doing their own MRV in-house presents a conflict of interest and could lead to lower trust in MRV integrity and transparency. In the long run, do you envision Running Tide's MRV will be done by an external organization? And how do you envision the MRV process will work?
Yeah, I mean, I'm sympathetic to that perspective. I think that everyone wants there to be like a lot more governance on this. And we've seen, a lot of kind of like MRV companies enter the space. But again, MRV means a lot of different things, right? And so there are parts of measuring this system which are like so unique and boutique to the actual intervention. It's really hard for me to imagine them being placed into some sort of like cookie cutter service provider. I mean, when we developed our, offshore drifting instruments, we spoke to a lot of service providers saying like, this is what we're trying to do. Do you have instruments that can help us here? And and the fact is, like, you're trying to get carbon removal to happen with an excellent margin. I'm sorry, I think there's some chatter on the line here.
Yeah. Sorry, I just
I think you're just never going to get that marginal cost where it needs to be without having these like very, very specialized instruments. Now, that's one piece of the puzzle, right? We would love to see more governance mechanisms to audit. And when here I mean audit, I really mean like analyze the the actual like ocean science analysis that we do in order to identify like how robust it is. We would love to see, for example, I think we teased apart a little bit in the talk the difference between making an intervention and then looking at the perturbation that results from that intervention and how that unfolds through the Earth system. That second thing I think is a lot easier to kind of imagine how that might be kind of like maybe an open source whole of community toolkit that has a ton of governance. And how we build there, I think we're just going to have to take it one step at a time. So I guess in an answer to Veronica's question, like it's going to, I think, have to be split down the middle at some point. There are just certain things here that are not going to be efficiently broken out into a third-party mechanism, and you're just going to have to rely on audit the way that many other industries do.
Thanks, Max. I want to come back to a question that Mallory Ringham asked earlier about Running Tide's current carbon capture capacity. As lots of these technologies are moving forward, we're starting to hear that folks are doing things at the kilogram scale, and then at the ton scale, and then tens or hundreds of tons or kilotons. And so where is Running Tide in terms of your technology development and capacity to capture carbon?
Yeah, so we're at the thousands of tons scale. And the reason for that is, primarily because of these ecological constraints that we've talked about. We are very much structuring our deployments in this iterative scale of, small deployments in order to kind of span the space in time and space of a deployment region, in order to get a lot better at this ocean transport problem. And as I identified, we need to be able to elongate that flotation period, flotation duration, in order to really see that macroalgae growth. And so until we can do that, we are in this sinking of terrestrial biomass column, right, which just doesn't give you that mass transfer leverage that you get when you're starting to do photosynthetic fixation in the ocean.
Thanks, Max. Let's ask one final question, which is slightly more on the technical side, but it has to do with the fact that there's been an increasing recognition of the role that dissolved organic matter and dissolved organic carbon can play in carbon sequestration in the ocean. And the question is what running tide accounting for dissolved organic matter released during the macroalgae growth and sinking?
Yeah, so I mean, this is what I was getting at when I said that what we're doing right now is like Stone Age technology, right? So, there are so many questions about like how MRV is going to work, how ecology is going to work. And we're in a place where we, foundationally are just trying to build trust within the industry. And so for that reason, we are doing the most straightforward thing that we can, and the most easily measurable thing that we can conceive of. So we are right now, just when it comes to macroalgae, intending to count the intact macroalgae that is attached to a carbon buoy at the time that it sinks. Yes, we are very aware that the ultimate capacity, like maximum capacity of carbon removal will scale dramatically when you can get to this flux of not just dissolved organic carbon, but even just particulate organic carbon that breaks off. So we need to know a lot more about, how labile or recalcitrant that material is, and what its lifetime is, in the surface of the ocean and in the mixed layer, before it propagates down to the deep sea and can be counted as sequestered. But when we often say at Running Tide, like, this is what we're doing right now, but the final solution of, the final architecture, that gets us to, to these gigaton scales is either going to be, substantially larger or substantially smaller. And that this is the version of substantially smaller, right? Well, what you're really doing, and this makes the most intuitive sense to me from an Earth system perspective, what you're really doing is stimulating that flux of organic carbon. And, so much of that flux of organic carbon is going to be DOC and POC. And so being able to account for it is the key there, I think.
Thanks, Max. We are approaching the top of the hour, and so I'm hoping that the audience can join me in giving a really warm, genuine round of applause and thanks for Max for spending the last hour walking us through Running Tide's process.
Yeah, thank you all. I mean, I'm sure I created more questions than answers for a lot of you. So I don't know, David, if there's some way for people to follow up through Ocean Visions, we'd be happy to just, close the loop.
Yeah, that's great. I think maybe one other option, Max, would also be to drop your email in the chat if folks want to follow up directly with you.
Sure. Yeah, I can do that.
Thank you. I want to say again, thanks to Max, and also that this is going to be the first in a whole series of webinars that we will be announcing over the next few months, where we're going to be featuring teams from our Launchpad program, where they're talking about their science and technology and environmental impact assessment program. So keep your eyes peeled for announcements about future webinars. And if you heard what you liked today and are really interested in trying to get some of the technical advising and assistance that Max referenced throughout his talk, please consider applying for the Launchpad. Nikhil has dropped the link in the chat, and the first step in the application process, the deadline is tomorrow. So please pay attention to that. And otherwise, I hope you all have a great day, and I look forward to seeing you all soon. Thanks again for tuning in.